Good morning, class. My name is Steve Bamshede Samson. I'm the e-tutor for this particular course, Assembly Language. We are in Section 1, Course Unit 3. And the objective of the course still remains the same thing. The assembly language remains the same thing. Then, in this particular unit, it is expected for us to, at the end of it, we should be able to define instruction sets. Mentioning the type of instruction sets, we should be able to do that at the end of this particular section. So, instruction sets. An instruction set architecture is part of the abstract model of a computer that defines how the CPU is controlled by the software. It also acts as an interface between the hardware and the software, specifying both what the processor is capable of doing at a particular time. What we are simply saying is that instruction sets is an abstract model of a computer that defines how a CPU is controlled by software. Which software? We are talking of operating system, application software, and other software. How the CPU is being controlled, managed. It is the work of instruction sets. It also acts as an interface between the hardware and the software. Look at it. When we say operating system is the interface between an hardware, you can see when we are now breaking it down again, it is the interface between instruction set is the interface between the software and the CPU itself, specifying both what the processor is capable of doing at a specific time. So that comes to the description of instruction sets. How do we describe an instruction set? An instruction set is a group of commands for a central processing unit in machine language. The term can refer to all possible instructions for a CPU or a subset of instructions to enhance its performance in a certain situation. All CPUs have instructions sets that enable commands directing the CPU to switch the relevant translators. The instructions tells the CPU to perform tasks. Some instructions are simple read, write, move command that direct data to different hardware elements. So we said description of instruction sets. When we make reference to description of instruction set, we are saying that an instruction set is a group of commands for a central processing unit in a machine language. The term can refer to all possible instructions from a CPU or a subset of instructions to enhance its performance in a certain situation. All CPUs have instruction sets that enable commands directing the CPU to switch the relevant transistor. The instruction set tells the CPU to perform tasks. Some instruction sets are simple read, write, and move commands that direct data to different hardware elements. The instruction sets are made up of a specific number of bits. For instance, the CPU's instructions might be what? 8 bits, where the first 4 bits makes up the operation code that tells the computer what to do. The next 4 bits are the operand, which tell the computer the data that should be used. If the instruction set of a CPU is 8 bits, the first 4 bits makes up of the operation code. The kind of operation that it wants from the code that is attached to it. Then the next 4 bits are the operand, which tells the computer the data that should be used. So the length of an instruction set can vary from as few as 4 bits to many hundreds. Different instructions in some instruction set architecture have different lengths. Other instruction set architectures have fixed length instructions, which takes us to the classes of instructions. So in the classes of instruction, we said the x86 CPUs provide 20 basic instruction classes. 7 of these instructions have 2 operands. 8 of these instructions have a single operand, and 5 instructions have no operand at all. The instructions are move, 2 forms, hard, soft, command prompt, and or not, G, Jin, JB, JBE, JA, JAE, GMP, BRK, irate, hot, get, and put. The following paragraph describes how each of these works. Do you get me? So, the following paragraph do what? It describes how each of these works. Move, reg, register, reg, memory, reg/memory/constant. Move memory, comma, reg, where reg is any of AX, BX, CX, or DX. Constant is a numeric constant using hexadecimal notation, and memory is an operand specifying a memory location. The reg/memory/constant operand tells you that this particular operand may be a register or memory location or a constant. Do you understand what they are trying to say there? So let me finish this. The add instruction add the value of the second operand to the first register operand, leaving the sum in the first operand. The sub instruction subtracts the value of the second operand from the first, leaving the difference in the first operand. The command prompt instruction compare the first operand against the second and save the result of this comparison for use with one of the conditional jump instructions described in a moment. D and OR instruction computes the corresponding bitwise logical operation on the 2 operands and store the result into the first operand. The NOT instruction inverts the bits in the single memory or registered operand. The control transfer instruction interrupts the sequential execution of instructions in memory and transfer the control Are you there? Transfer the control to some of other points in the memory, either unconditionally or after testing the result of the previous command instruction. This instruction include the following. If you look at it, the first 6 instructions in the group let you check the result of the previous CMP instruction for greater than or greater or equal or less than or less or equal or equality or inequality. For example, if you compare the AX and BX registers with the CMP instruction and execute the JA instruction, the x86 CPU will jump to the specific destination location if AX was greater than BX. If AX is not greater than BX, control will fall through to the next instruction in the program. The JMP instruction, unconditional transfer control, to the instruction at destination address. The instruction return control from an interrupt service routine. The get and put instruction let me read and write integers value. Get will stop and prompt the user for hexadecimal value and then store that value into AX register and put delay in hexadecimal the value of the AX register. So now, number 2, arithmetic and logical instructions. Add, sub, and, or, X, or, not, inc, dec, CMP, nec, mod, mol, im, mol, div, id, text. Arithmetic instruction like addition, subtraction, multiplication, division, and logical instruction like logical and logical or logical XOR or complement are part of this group. Add reg, add reg, men, add men, reg, add. So if you look at it, then reg AX, command BX, CX, DX. Which we look at in the memory variables. Then immediate 5, minus 24, 3F. So this takes us to the after operation between operands. The result is always stored in the first operand. A CMP and a test instruction affect flag only and do not store a result. These instructions are used to make decisions during program execution. They only affect the following flags: CF, ZF, SF, OFF, PF, AF, and 23. Add second operand to first, subtract second operand to the first, then CMP subtract second operand from the first for flag only. For multiplication, div and idiv flag are undefined, but mul unassigned multiply when operand is what? Is a byte. double column AX equals to AL multiplied by operand. When operand is a word, AX is equal to AX multiplied by operand. If the source operand is a byte, then it is multiplied by register AL, and the double length result is returned in AH and AL. If the source operand is a word, then it's multiplied by register AX, and the double length result is a return in register DX and X. So these are simply the diff unsigned define, then when operand is a word, and when IDF sign divide, and when operand is also a word. So these are simple. So to declare a label in your program, are you with me? Just type its name and add double column and full column. No, sorry. Just quote a double column. Simple. Quote a full column to the end label. Can be any character combination, but it cannot start with a number. For example, here are three legal label definitions: label 1, label 2. A label can be declared on a separate line or before any other instruction. For example, look at the example there. So then here is an example of jump instructions as it is described in this simple code. This takes us to the type of instruction set. Type of instruction set. If you have complex instruction sets computer, which is CISC or CISC, then complex instruction set computer processor have an additional microcode or programming layer where instruction acts as a small program. Programmable instructions are stored in fast memory and can be what? Updated. More instructions are included in complex instruction set computer than in other type of instruction set. A single instruction can initiate multiple actions by the computer, such as single add command, launching multiple memory access, load and store instruction. I hope you understand that. Let me take that. I say more instructions can be what? Can be included in complex instruction set computer than in other type of instruction set. And a single instruction can initiate multiple actions. A single instruction, a single directive can initiate multiple actions by the computer, such as a single add alone command, launching multiple memory access, loaded and store instruction. You understand what I'm saying? It can run multiple distance. So reducing instruction set risk architecture are hardwire control It does not require microcode, but has a greater base instruction set. RISC also use a smaller and more compact instruction set with a fixed instruction format. Reduced instruction set. So RISC processors are also designed to process faster and more efficiently. Then we have enhanced instruction set. These instruction types are more familiar because they are often used in marketing CPU. Example of this goes back to the 116 MHz Intel Pentium with multiple media extension technology. It was introduced in 1996 and marketed with enhanced Intel CPU multimedia performance, referred to the extended instruction set. So this is the one they use in describing the size of processor, what the processor capability of the processor is normally used. So from there, from this 116 meg, we move to gigahertz. When we start gigahertz, we have processor that is called 1.2. We have 2.0 gigahertz. Then we have 3.0 gigahertz. If you have 3.0 gigahertz processor, then your system will be very fast. But now we now have dual core, whereby a multi-processor is in one single computer. So how are instruction set command used? How do we use instruction set command? If you have to use them. Number one, data handling and memory management. Instruction set command are used when setting a register to a specific value, copying data from memory to a register or vice versa, and reading and writing data. Then you have the arithmetic and logic operation and activities. These commands include add, subtract, multiply, divide, compare, which examines value in two registers to see if one is greater or less than the other. Control flow activities. One example is branch, which instructs the system to go to another location and execute command there. Another is jump, which moves to a specific memory location or address. So, in conclusion, we have been able to at least learn that instruction set is used to list all codes and instructions for a processor. Then we have also been able to, in summary, we have been able to at least cover the various classes of instruction sets with specific examples. The various type of instruction sets and command used. So with that one, many of you can now start making use of your assembly language and see how you can at least carry out set up different instructions for your processor.